All right, we're gonna move on and talk about set operations, which is section 2.3. Okay, so maybe. Oh, hold on 1 second. My tablet is not plugged in. All right, there we go. So we are going to look at set operations. So basically, we're looking at ways to, in most cases, combine two sets by some operation and get a third new set. We've actually at this point looked at one operation which works on a set, and that was complement of a set. You take the complement of a set, you get a new set. Everything else but what was in the set you're taking the complement of. So technically that is one operation. So the ones we're going to look at today we'll consider to be binary operations, in that we will take two sets, combine them by a certain operation, and get a third new set. All right, so it's their fourth. First one. Maybe spell it. Intersection. All right, so I'm gonna put this in set notation. All right, so it's designated the operation. So we have sets A and B. We're going to note this operation by a capital upside down U, and this is read A intersect B. As soon as I see that. So what comprises A intersect B? So you set builder notation. So we want all elements X such that X is an element of A, and this is the key word, and X is an element of B. It's everything that is in A and B. So to be in the intersection, you have to be in both sets. So let's do a Venn diagram. So I've got a set A and a set B. So for universal set, everything out here in the box, we've got a set A and a set B. So we want to shade what would be representative of the elements of A intersect B. It's what's common to both. So we want to shade where these two circles overlap. That would be A intersect B. Any questions there? All right. Next operation. Union. Sets. So let's say we have a set A and a set B. Note this with a capital U turned upright, not upside down. A union B, and it's read A union B. Now here, we're going to want all elements X such that X is an element of A, keyword or. X is an element of B. So when you hear the word and, you know you're talking intersection. When you hear the word or, you know you're talking union. So an element could be in both A and B, but at the least it has to be in one or the other. So I always think of union as just taking your two sets and dumping them together in one big hat. So if we drew a Venn diagram of this situation, what I would end up wanting to shade is everything in A or B. That would be the Venn diagram for union of sets. Questions on that? Right? Difference of sets. All right, so here we hear the word difference. We do think subtraction, and it looks like a subtraction symbol. So when you see this, we know we're dealing with the difference of sets. Now, this is actually read A, not B. And it's right in those words that we can figure out what elements are going to belong to this set. So A, not B. We want all the elements X such that X is an element of the set A, and that it is not in B. That is, if I see A not B, give me everything that's in A, except I'm going to toss out the ones that also are in B. Draw a Venn diagram. This set. So if this were A and this were B, I would shade just a portion of A that's outside of B. So won't shade anything that includes B. So that portion. Questions on that one? All right. Okay. Next set, I can't use a Venn diagram to represent though, but this is going to be an important set. Now, officially, it is known as the Cartesian product of sets. Word Cartesian is a guy's name, Rene Descartes. So it's named after him. We'll look at a few other connections here in a second. Now, I see product, makes me think multiplication. And the notation certainly looks that way. So it is represented this way. So it looks like I'm going A times B. Now these are sets, A and B. And this is read, like this is read A not B. This is read, just read it A cross B. So A cross B. And you can just say, you don't have to say, you know, hey, I've got a Cartesian product of these sets. So that's officially the name. You could just say, this is the cross product of these sets. Now, the reason you cannot use a Venn diagram is the nature of what an element looks like in a cross product. It's an ordered pair. It's all the ordered pairs A, B, such that A, little a, comes out of the set here, and little b comes out of the set here. So when we hear the word ordered pair, pairs two, ordered means they are in a particular order. So I'm not going to think coordinates here right now. Just think component. First component, second component. First component has to come out of the set here. This is read left to right, out of the one on the left. Second component comes out of the one on the right. But it is a set of ordered pairs. So if I were to look at an example here, let's say I've got a set A, let's keep it simple. It's got the elements 1, 2. Set B, let's have the elements 3, 4. So if I said find A cross B for these two sets. All right, I'm kind of running out of room here, so, but there would be 4 ordered pairs. It would be 1, 3, 2, 3. Down here. 1, 4. And 2, 4. Now this would be completely different than B cross A. B cross A would be the ordered pairs 3, 1, 3, 2, 4, 1, and 4, 2. Again, the component on the first component of the ordered pair comes out of the set on the left, as you read left to right. Ordered pairs are only equal if their components are exactly the same. Since these are reversed, these sets are what we would call disjoint. They have nothing in common. So, glean from this, we can actually glean using a little inductive reasoning a couple things about this. First off, in general, cross product is not commutative. Like regular addition, regular multiplication is a commutative operation. I can multiply 2 times 3, and it's the same thing as 3 times 2. I can go 2 plus 3, and that's the same thing as 3 plus 2. Cross product, not a commutative operation. But there is something that is common to both of these, and that is the number of ordered pairs that I get. There are 4 ordered pairs here. The cardinality of this set would be 4. There's 4 ordered pairs here, and the cardinality is therefore 4. So what is the same is that the cardinality, the number of ordered pairs I get out of A cross B, that is the same as the cardinality of B cross A. And even more than that, squeeze this in here somehow, is that can be found simply by multiplying the cardinalities of each individual set. That is the cardinality of A times the cardinality of B, which would also be the cardinality of B times the cardinality of A, since multiplication is commuted. So that is, if I gave you a set, you had a set A and it had a cardinality, you had a set A and it had a cardinality of 8. And you had, for example here, and a cardinality set B, and it had a cardinality of 56, then I would know without writing them all down that the cardinality of A cross B or B cross A would have to be 56 in that example. Or I wanted that to be a 7, so that 8 times 7 was 56. Right. So, wouldn't be, it definitely would not reasonable to have you write down all 56 ordered pairs, but you would know that there would be 56 of them. Second up. Closed out my math lab. Right. Any questions on that thus far? Okay. So, page. So, when we look at, we learn how to graph in basic algebra. What do? We graph on what we call a rectangular coordinate plane. And what this, what basically we do to form the rectangular coordinate plane is take two real number lines. That is a line here representing the set of real numbers, any numbers that are rational or irrational, and a vertical line. That is, it is going to hit this one perpendicularly at each of their, what we call origins, or at 0. And we will sometimes refer to that as x-axis, and that is y-axis. And then we can plot, ordered pairs. So say here's 2, 3. So that would be 2, and that would be 3, et cetera, et cetera. At the end of the day, officially, that rectangular coordinate plane is referred to as the Cartesian coordinate plane. And what really is the Cartesian coordinate plane? It is the set of real numbers crossed with itself. Let's put it in context of sets. It's the reals crossed with the reals. And we can now say that the set of real numbers, just the set of real numbers themselves, is the union of the set of rationals with the irrationals. That is, the rationals union with the irrationals is the set of reals. All right. All right, so one other thing out of this section that we need to cover. Look at some examples. Something we're going to call De Morgan's. It's for Augustus De Morgan. De Morgan's laws. All right, and there are 2 of them. Let's say I took 2 sets and I intersected them. So I found out what the elements they had in common. And then I took the complement of that, which would be everything but what's in that set. It is the same thing that if I first took the complement of A and then union that with the complement of B. So where this will prove useful when because you're going to have exercises where you're asked to find elements of a set, and there's going to be multiple operations to perform. And if you do so, you can do it either way. You get to the same place. That's what we're saying. They are equal. But if you would do this one, you're really got to do three things. You're going to have to first take the complement of A, you're going to then take the complement of B, and then you're going to put those two together via union. Here, it's really two things. Find out what they have in common. That's one thing. And then just write down everything else. And that would, the complement of it. So you would only have to do two things. Right. There is also one other thing that goes with De Morgan's law, and it is this. And pattern-wise, this would make sense. If I would union the two sets and then take the complement, it would seem reasonable based on what we've seen in this first one, that I could take the complement of A and then flip this, just like it was flipped here, that is intersected. And so those two collectively are known as De Morgan's laws. Now, this can be expanded, incidentally, like to multiple sets. If I put inside here through another intersect C, then you would union here with a C complement. Or if I had A intersect B, intersect C, intersect the set D, and then took the complement, I could then write A complement, union B complement, union C complement, union D complement, et cetera, et cetera. This will expand out to as many sets as you want to put in it. All right, any problems that you would deal with here in this section will just be dealing with two sets. Okay, so that's everything that I needed to get covered, I do believe. But what we want to look at now, first off, make sure there wasn't anything else I needed to talk about. I don't believe so. Okay. Let's do some examples with set operations. So let's say I've got a universal set, and it's got the elements A, B, C, D, E, F, and G. And then living within this universal set, let's say I've got a set X, and it's got the elements A, C, E, and G. And a set Y, capital, and it's got the elements A, B, C. And a set Z, and it's got the elements B, C, D, E, and F. All right. So we're going to go through and look at doing some set operations. We'll look at a few first, just single operations, determining what elements would be in them, and then we will look at combining operations. So number one. Two. Let's do number three. And I'm going to throw in a number four. Put in them right here. All right, what I want you to do, take about a couple minutes. I'm going to go warm my coffee up. You're going to write down the elements that would belong to the set for each one of these. So I'm putting the brace here for you. So put in the elements and then close with the brace. So jot those in your notes. You don't have to type them in chat or anything. Just work on them. I'm going to go grab a coffee, come back, and then I'm going to give you the answers. But you first try to come up with what you think the elements are for those four. All right, I'll be right back. All right. All right, so I'm going to go ahead and jot down what elements would belong to these four sets. So in all four problems that I put up here, they are single operations. Then we'll look at some multiple operations ones here later. So the first one, you see it's intersection. So you just automatically know, find what's common to both sets. So we've got them here. And when I look, what's common, it's the elements A and C are common to both. So that would be what you should have had, and separate the elements with a comma. So it's the set with the elements A and C. This one is complement of, so it's everything in the universal set except what's in X. It's everything else, which in this case, since this X had A, C, E, and G, the complement would have B, D, and F, everything else. Good there? All right, so the next one. This is set difference. And so again, read X, not Y. So reading left to right. First off, when you see a set difference, you know the elements of what you come up with have to be an X, the set on the left. It's just if there's anything that is also in Y, I throw those out. If the sets are disjoint, it's literally just the set X. So in this case, X and Y, we knew from what? Number one had what? A and what? C in common. So those are the ones I'm going to toss. So what would be an X not Y? Well, E and what? G. E and G are in X, but they're also in Y, or excuse me, are not in Y. So those, I would be tossing A and C. No. Yes. Be tossing out A and C, the two that were also in Y. Anyway. So I wanted to give it just so number 4, the reason I did this, I went and looked at Y not X just to make sure we got set difference down. So this time I want to write down the elements that are in Y, throw out anything that happens to be what in X. So in this case, X has what, A and C. So what's that leave me with? Just that's it. So when you do a set difference, your starting point is the set on the left. And then it's just a matter, do I throw out any elements that happen to be in the set on the right? Questions on those 4? All right. So let's do some problems where we are combining elements. So we're still working with these sets. Let's do X complement intersected with Z. All right. So just like you were working an arithmetic problem, I want to go step for step for step. And it works much like, order of operations. Work inside grouping symbols first, evaluate exponents, and then, addition, subtractions, multiplications, or multiplication, division, addition, subtractions. So all I'm going to do on this first step is take the complement. I'm not going to try to do everything at once. So the complement of X, we know from what we did here, is BDF. It's everything except what's in X. So B, D, F. And then I'm going to intersect that with set Z. So then I can look here and I can look here. What do they have in common? It's BDF. That's what these two have in common. And done. All right, questions on that? Let's look at another one. Let's do X complement intersected with Y complement. Now we don't have to change anything here. I could just shoot straight at it, but I do recognize this as one of De Morgan's laws. And so I'm going to first just rewrite this as X union Y complement. So I only actually have to do 2 things as opposed to 3. Now, so I applied De Morgan's law. So what I'll first down is write what is in the union of X and Y. Remember, you just throw everything together in a big hat. So you would have A, B, C, D, and G. That would be X union Y. Still have to take the complement, which would be then write everything else down. So what would that be? Looks like just what? D and F. That would be it. Questions on that one? All right, let's pull out all the stops here. Whole kitchen sink. Let's find this set. Z unioned with X complement. And then we're going to take the complement of that. Oops, didn't want it. Yep. And we're going to intersect that with Y. All right, so there's a lot going on with this one. So again, step at a time, work on innermost grouping symbol, kind of evaluate exponent, which in this case, analogously would be the complement. So all I'm doing to start, as I work this thing out, is I'm going to find X complement. That is it, one thing. So X complement was BDF. All right, so now I can union Z and the set BDF. So here's Z. BDF is in there. Those three elements are in there already. So union them up, you're just going to get Z. And you can shorten your workload since Z union with this is Z. That is, it's these elements, B, C, D, E, F, throw them all together. I'm just going to write Z. Still want to take the complement of that though, and then intersect with Y. All right, so Z complement would be just A and G. And then I want to intersect that with Y. So Y has A, B, C. This is A and G. So the only thing in common that they have at the end of the day is the set with just a single element A. But again, a step at a time here with these. Okay. All right, you're going to have a few other problems dealing with Venn diagrams. So those are the last two examples I need to make sure we look at today before we leave. Okay. So here's going to be our problem. I'm going to shade a Venn diagram. That would represent represent the following set. And our set is going to be what? That looks like a good one. The set A intersect B complement, and then intersect C complement. All right. So here we go. So what I'm going to give you is and this, if you hit, show me an example or help me solve this on one of these problems, they may not do it this way. I'm going to give you a systematic way to figure out what to shade. It does require that you know the set operations, though, and what they do. So the first thing I'm going to do is draw a Venn diagram with 3 sets. So if you have it at 3 sets within a universal set, so you'll draw yourself big box representing universal set. So if you had 3 sets within a universal set, three interlocking circles looks like that. So next class, it gets a little, I'll show you a 4 set one. I'm not going to draw it today. You can't use 4 interlocking circles. You got to use 2 circles and what looks like 2 kidney beans. They are because you got to have 16 different regions. Notice there are 8 regions now. So it goes by powers of 2. We have seen that before. If you have just one set in there, you've got 2 regions, the circle itself and the region outside that circle. So what I'm going to do is, so I'll label the sets A, B, and C. I'm going to number each region. Now this is, you don't have to number them like I do. It's just you need to have a number 1 through 8 in each of the 8 distinct regions. So I'm going to just go across the board. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 regions there. Now just need to figure out what to shade. So what I do is I come over here and I'll say, well, I've got A. I'm going to have to work with it. I don't put an equal sign or put braces here. I'm just going to put an arrow and say, okay, what regions would comprise A? That's 2, 3, 5, and 6 by my numbering. And what regions would comprise B complement? Remember, that's everything outside of B. Well, that would be everything outside of B would be regions 1, 2, 5, and 8. All right, with me so far? All right, so then what's it want me to do? It wants me to intersect the 2. So A intersect B complement. This would be the regions they have in common. And so when I look now at these 2, that looks to be regions what, 2 and 5. All right. All right, we got more going on here. Then we're going to take that and intersect it with C complement. So let's write down the regions that belong to C complement. That's everything outside of C. That would be regions 1, 2, 3, and 4. So finally, and we're there. This, which we figured up to be regions 2 and 5, we want to intersect with C complement, which we now know is regions 1, 2, 3, and 4. They have in common 2, and that is it. That is, and here's 2. So I now know what to shade. So I kind of covered up my 2. It was right there. So region 2 was where I ended up shading. But you can kind of tell that because I've got all the other numbers there. Good. A lot of the problems that you're going to find that look like this, you're going to have 4 multiple choice answers. So if you just construct it this way, then then you'll know which one to pick. Okay. Now, just let you work on that one and then bring that question back on Wednesday. Okay. So pretty much hit all the examples I need to. We're going into the exercise set itself. Sure. Okay. It's one of those. They put some homework problems. There's some homework problems in 2.3 that this really isn't officially addressed until 2.4. I'm going to go ahead and talk about it now so you don't have to sit and stress about it. And this is really going to be on the homework question 11, 12, pretty much 11 and 12. Now remember, this means cardinality. So it is a number, number of elements in that set, number of elements in A plus the number of elements in B. And we would say, okay, is that always true? It seems reasonable. But as it turns out, there could be a problem here. And the problem is this works fine here if A and B are disjoint. If they have nothing in common, this is true always. But if A and B have something in common, then when you do this, it's going to be off by that number of elements that they have in common. Because what will end up happening is you'll count twice on the right-hand side. So what we can do, so this right here is true if the intersection is empty. That is, they're disjoint. They have nothing in common. So if their intersection is not empty, if they have something in common, to make this always true, so we don't double count anything, then on the right-hand side, I'll just take away the cardinality of their intersection. That is, I'll take away the number of elements that are common to both. And this then is always true for any sets A and B. All right. A couple problems. Some cross product stuff. That. When you get to the problems where you have to shade the Venn diagrams, you'll click on, so just procedurally, you'll take your cursor, click on the Venn diagram, and you're going to get a toolbar, and you'll see a paint tool, and you click on that paint tool, and then you can go in and click, and you have to, so if you've got multiple regions you have to shade, you'll go down and click the paint tool each time, click the region you want, you'll see it shade like a yellow color, and that's how you shade it if you have to actually shade them. And there are a couple problems where you'll have to do that. And then there are some multiple choice ones as well. Questions. That is it. All right, so I'm assigning 2.3 for next class. So that would be 13th. And it is assigned. So next class on Wednesday, I will, we have one section left to cover. And at that point, we'll we will be ready for our exam. There is some other set material that I'm going to go over after I make these. So I will go over 2.4 next on Wednesday. I will assign a quiz that goes through 2.1, 2.2, 2.3, what we have covered up to today. I'll go over 2.4, assign that homework. So basically on Wednesday, I will be assigning that second quiz and 2.4 homework. On the following Monday, I have some set stuff I want to go over about infinite set, though I'm not going to have anything on the test with it. I will be assigning on Monday after we review the second exam, and we will be ready to move ahead to numeration and number theory. So any questions?